In this video, we are going to take a slightly more in-depth look at the concepts of parallelism and unfolding as they can be applied to certain kinds of signal processing algorithms. As an example, we'll take up a simple FIR filter defined by the equation y of n equals a times x of n plus b times x of n minus 1 plus c x of n minus 2. The direct form 1 or the standard implementation that we are normally familiar with would look something like this. The input would be x of n. By putting it through a delay element or a register, we would obtain x of n minus 1, and one more register would give us x of n minus 2. Now, of course, we need to multiply by the coefficients. So multiply by a, multiply by x of n minus 1 by b, and x of n minus 2 by c. And now we need to add the results together, which can be done using a chain of adders like this. In other words, it's quite easy to see that this particular figure implements the equation that we have shown over here. All right, now what is the critical path corresponding to this equation? As we know, that essentially corresponds to a path that looks like this. It has one multiplier delay and two adders as part of the critical path. An equivalent path, of course, is this one. But the third path, which is this, is actually a bit shorter. This is only Tm plus Ta, whereas the other one as well is Tm plus 2 times Ta, right? So the critical path of this determines the minimum clock period that can be used on this system, and as such that would determine the sampling rate that can be applied to this FIR filter, which means that if my sampling rate is greater than or equal to Tm plus 2 times Ta, it means that the maximum sampling frequency permitted for this architecture is going to be determined by 1 over Ts. Now, one of the things that we are interested in is to see what is the highest possible sample rate that we can use for a given filter or a given algorithm or a given problem, and to find appropriate architectures that will allow us to increase that sampling rate. So if that is the case, one of the possible changes that we can make to this given architecture is to try and reduce the critical path by means of introducing additional registers between the multipliers and some of the adders. That process is known as pipelining and is discussed elsewhere. So in this particular video, I'm not going to get into any further detail on that. What we are going to do instead is to understand in a little bit more detail how the concept of parallelism can be applied to this particular filter to improve its throughput or sampling rate, and how that concept of parallelism can be generalized in terms of something called unfolding, which can be applied generally to any kind of data flow graph, not just to FIR filters. So the basic idea of parallelism is quite simple. Essentially what we are saying is, I know that the equation y of n equals a times x of n plus b times x of n minus 1 plus c times x of n minus 2 allows me to compute one particular value of y of n. Now, what if I rewrite this in terms of a new index variable that I will call k and write it as y of 3k equals ax of 3k plus b x of 3k minus 1 plus c x of 3k minus 2, y of 3k plus 1 will therefore be equal to a x of 3k plus 1, which is exactly the same as before, b x of 3k plus 1 minus 1 which I can rewrite as just 3k itself, and c into 3 x of 3k plus 1 minus 2, which is 3k minus 1. And similarly, y of 3k plus 2 will be equal to a x of 3k plus 2. In other words, I'm just using the substitution. Instead of n, I replace it with the value 3k or 3k plus 1 or 3k plus 2. B x of 3k plus 1 plus c x of, in this case, 3k. Now, the interesting thing about these three equations is you'll notice that there are some terms that are common over here. In other words, there is an x of 3k here, here, as well as here. There is an x of 3k minus 1 in these two places, an x of 3k plus 1 in these two places, and the last two terms, in other words, the x of 3k minus 2 and x of 3k plus 2 are only used once in this equation, in the set of equations. So how does that help us? We can try to draw a simple unified architecture that combines these three equations and implements them such that with a minimal number of extra registers but with additional hardware, we are now able to implement all three equations in parallel. How will that help us? It will essentially allow us to compute three values, y of 3k, y of 3k plus 1 and y of 3k plus 2, all at the same time in parallel, under the assumption that every one of these terms, x of 3k minus 2, 3k minus 1, 3k, 3k plus 1 and 3k plus 2 are somehow available to me or have been stored somewhere in some kind of shift register. What does such an architecture look like? Let's try and draw out how this could be implemented. So in order to understand how this business of writing the input as, or rather the output as three separate equations helps us, we need to first think of something called a serial to parallel converter, which allows us to visualize what exactly is happening with the samples x of n. If we draw out a timeline where we say this first value corresponds to x of 0, the second value corresponds to x of 1, and so on, then what we can essentially say is we are putting this through something which we will call a serial to parallel converter. In other words, the input going in over here is serial. It is one sample after another. But what comes out of this serial to parallel converter is three different streams of data. What comes out on the first one is x of 0, then x of 3, x of 6, x of 9, and so on. On the second stream of data, you get x of 1, x of 4, x of 7, and so on. And on the third, you get x of 2, x of 5, x of 8, and so on. Now, what have we achieved by doing this? Effectively, the important observation over here is that if the time interval between samples over here was equal to t, then the time between samples that is required over here is going to be 3 times t. Because x of 5 is followed after 3 original sampling in periods later by x of 8, which means that the stream which carries x of 2, x of 5, x of 8 is changing only at 1/3 the rate or frequency of the original input sample stream. Now, why is this useful? It basically means that any register or any combinational circuit into which these symbols are being fed needs to be able to process things only at a rate of 3t. That is to say, it can have a considerably longer critical path and still manage to complete its computation within the time that is allowed for the next sample to arrive. The question that now comes up is, now that we have managed to split the input into 3 distinct streams, how do we make use of this information? You can observe on the right over here that each of these streams essentially corresponds to x of 3k, x of 3k plus 1, and x of 3k plus 2. In other words, when k is equal to 0, we get x of 0, x of 1, and x of 2 on the three streams, as we can see on the first column of data. When k is equal to 1, we get x of 3, x of 4, and x of 5, and so on. Right? Now, in addition to this, the next observation that is useful to make is the fact that if I have a stream x of 3k which has the values x of 0, x of 3, x of 6, and so on, what happens if I put this through a single delay element? Remember that the clock being fed to this is a 3t clock. In other words, it has a time period of 3t. Why? Because the interval that we have over here itself is going to be 3t. This is the time period for this slowed down stream. So if I have a register with this slow clock applied to it, what I'll find is that after applying this delay, effectively what I get over here is going to be the sequence x of 3k minus 3. Recall that if I had a simple register, that is to say, if I just had x of n going through a regular register which is sampled at t, what I have at the output is effectively a sequence which is x of n minus 1. Right? In other words, it corresponds to the previous sample. What we are saying is that by analogy, we get the same behavior over here. We can think of it as x of 3 into k minus 1, which is x of 3k minus 3. In other words, we have the sequence x of minus 3. This sequence x of 3k minus 3 will basically have the values x of minus 3, then x of 0, x of 3, x of 6, and so on. Right? So this effectively tells us that a single register being applied on the slowed down stream allows me to delay x of 3k to x of 3k minus 3. What that further means is that if I take the stream x of 3k plus 1 and put it through a register which is sampled at 3t, the output of this is x of 3k plus 1 minus 3, which is x of 3k minus 2. Similarly, x of 3k plus 2 fed into a sampling like this comes out as x of 3k plus 2 minus 3, which is x of 3k minus 1. Now, armed with all of this information, let's see what we can do with it and how we can use this in order to construct a 3 parallel version of the FIR filter that we started with. What we basically want is to implement these 3 equations. Y of 3k equals a times x of 3k plus b x of 3k minus 1 plus c x of 3k minus 2. Y of 3k plus 1 equals a x of 3k plus 1 plus b x of 3k plus c x of 3k minus 1. And y of 3k plus 2 equals a x of 3k plus 2 plus b x of 3k plus 1 plus c x of 3k. In terms of a hardware architecture, what does this look like? We can think of it this way. I have my x of n sampled at t going into a serial to parallel converter, and the output of this changes at 3t. So I have 3 streams: x of 3k, x of 3k plus 1, and x of 3k plus 2. which means that if I now go ahead and multiply each of these by appropriate coefficients, as shown here, where I'm basically multiplying them by A, B, and C respectively, the result that I get is going to be A x of 3k plus 2 plus etc., which as we can see from the equations is y of 3k plus 2. For the next one, what we want is that 3k plus 1 should be multiplied by A, 3k should be multiplied by B, and 3k minus 1 should be multiplied by C. Now how do we get 3k minus 1? By putting 3k plus 2 through a single delay element that is sampled at 3t. Add these together and the result is y of 3k plus 1. We can take this further to the third term, where we need to take x of 3k, multiply it by A, x of 3k minus 1 is to be multiplied by B, and we know that, as we already saw over here, this is going to be x of 3k plus 2 minus 1, or in other words x of 3k plus 2 minus 3, or in other words x of 3k minus 1. So coming back to this, what I have is the 3k minus 1 gets multiplied by B, and in order to get 3k minus 2, I need to take my input x of 3k plus 1 minus 3, which basically is x of 3k minus 2. Add these together and what we end up with is y of 3k. So the question that would naturally arise is, what exactly have we gained by this entire process, right? In order to do that, let's highlight the critical path that we have over here. We can essentially go through this path, which is Tm plus 2 times Ta, or equivalently through this, or equivalently through any one of a number of other paths also that works. All of these paths that are highlighted have the same delay, which is basically Tm plus 2Ta. Now, this looks as though it's exactly the same critical path as we started out with for the simple FIR filter. The crucial difference over here is, of course, the fact that we are now working in the domain of a slowed down version of the filter, which only requires this Tm plus 2Ta to be less than 3 times the original sample period. So effectively, even if we have slow multipliers and slow adders, which have a large value for Tm and Ta, all that we require is that the Tm plus 2Ta should be less than 3 times the original sample period that we are interested in meeting. When we put everything together, what does the final filter look like? What we could have is something like this. Our input x of n is taken into a serial to parallel converter. The input has a sample period of t, and everything after the serial to parallel converter operates at the period of 3t. There are 3 streams of data that essentially go into a block of hardware. The entire block essentially operates with a cycle period of 3 times t. At the other end of the block, we get 3 outputs, y of 3k, y of 3k plus 1, and y of 3k plus 2. And what we need to do is to put this through a parallel to serial converter which does the exact opposite of what a serial to parallel converter does. In other words, it takes 3 streams and multiplexes them into a single stream that has a data rate of t, or a sampling interval of t, which means that our input x of n as well as our final output y of n are now sampled at the same interval t, but the actual processing that is happening in between can happen at a much slower rate, in other words 3t in this case. How is this helpful? From the point of view of a VLSI designer, it means that if for some reason you are not able to construct hardware that is able to meet a very tight requirement in terms of a sampling period, the best way to solve it is by going parallel. You actually create n copies of your computation, split up the input into parallel streams, put it through a complicated block, but that block in between only needs to work at 1 by nth of the original input rate, and finally multiplex everything back together into the high rate that you need to process. In the special case of FIR filters, it turns out that using parallelism, you can also get a further benefit where you can actually reduce the amount of hardware, and rather than having n times the amount of hardware required for a single computational unit, you might be able to get away with less than that. Let's take an example with this equation. Y of n equals h0 x of n plus h1 x of n minus 1 plus h2 x of n minus 2 plus h3 x of n minus 3. I'm going to draw what's normally called the direct form 2 or the broadcast architecture for this filter, which would look something like this. X of n goes into h0, also into h1, but that is then sent through a delay element, h2, through 2 delay elements, and h3 through 3 delay elements. So in other words, effectively what we have over here is this y of n that we have over here takes h0 into x of n, h1 into 1 delayed version x of n minus 1, h2 2 delayed version, and h3 a 3 delayed version of x of n. In other words, it implements exactly the equation that we have above. Now, a 2 parallel version of this architecture could look something like this. So, if you are wondering how this architecture comes up, this of course corresponds only to the output y of 2k plus 1. Let's try and figure out how that happened. Let's take a look at this particular path that we have over here, which basically takes us and tells us that what we have is h0 into x of 2k plus 1. The next path that we have, this one over here, corresponds to h1 x of 2k. The next path would correspond to h2 x of 2k plus 1 minus 2 is equal to h2 x of 2k minus 1. And lastly, this path out here would essentially correspond to h3 x of 2k minus 2. Now, how did we obtain this? Notice that this delay element that we have over here is the only delay element that we are using in this particular path. But since it is working at a reduced sampling period of 2t, a single delay element effectively creates a 2 sample delay on the original input stream. Using this, you can verify that this particular structure that I have shown actually implements the y of 2k plus 1, and similarly a similar set of additions can be used in order to create y of 2k. So what we have done, in other words, is to take the input x of k, x of n, and split it using a serial to parallel converter into two streams, x of 2k and x of 2k plus 1. We finally obtain y of 2k plus 1 and similarly y of 2k, and we can merge them back together using a parallel to serial converter. Now, what's the hardware resource usage that we have over here? For y of 2k plus 1, I needed 4 multipliers and 3 adders. Similarly, for y of 2k, I will also need another 4 multipliers and 3 adders. What was my original usage over here? This one also required 4 multipliers and 3 adders. So effectively, it looks as though the 2 parallel implementation requires exactly twice as much hardware as the original implementation that I have. Let's see if we can construct an equivalent 2 parallel filter, but which requires lesser resources in order to compute the same amount of information. The way that we'll go about it is as follows. I'm just going to draw the final architecture, but what you will be able to see is that once you see the final architecture, you can then reverse engineer or understand exactly what was the motivation behind that architecture and how it came about. In other words, it's not something that came up by magic. It's more of an observation or an insight into the structure of the filter that we make use of in order to implement things like this. So what is this architecture? Essentially what it says is, I'm going to take the same two streams, x of 2k and x of 2k plus 1. And what do I do with them? The first thing that needs to be done is this needs to be multiplied by h0, and a delayed version of this will be multiplied by h2. In other words, what I have over here is h0 x of 2k and h2 x of 2k minus 2. Similarly, I will put this through another chain over here, which computes h1, or in other words, h1 x of 2k plus 1 and a delayed version multiplying by h3, which in turn computes h3 x of 2k minus 1. Add the two together. We will add these two together over here and add the h1 and h3 terms together over here. But now, before we add them together, in order to get y of 2k, I need to actually change this to h1 x of 2k minus 1 and h3 x of 2k minus 3. What's the simplest way to do that? Put a register here. Now, you might be wondering why go to all this trouble to create the structure, but if you at least look at it, it's not too far out of the ordinary. So far, nothing special or magical has happened. The trick really comes in the next stage, where we realize that some of the values that need to be computed in order to get y of 2k plus 1 have already been partially computed, and we can probably simplify our life by changing the way that we compute y of 2k plus 1. How do we do that? What we do is we take these values x of 2k and x of 2k plus 1, add them together, and now put this through another architecture that looks something like this. Now, this term that we have in the middle is interesting. What we can do with it is to basically consider the other two streams from the side. In other words, I'm going to tap off from here and subtract that term. Notice the plus and minus signs, and similarly also tap another value that I have over here, where I once again take a plus, but I subtract this term. The result is going to be y of 2k plus 1. How does that come about? Effectively, what we have over here, in other words, is x of 2k plus x of 2k plus 1 multiplied by h0 plus h1, delay at the sample rate of 2t, or the slower time period, which will basically give us this h0 plus h1 multiplied by x of 2k plus x of 2k plus 1 shifted by one sample period, which is x of 2k minus 2 and x of 2k minus 1. That term multiplies the h2 plus h3 coefficient, and if you work out the arithmetic, what you will find is that these two subtractors are effectively cancelling out those effects from what has already been computed in order to get the value of y of 2k. Now, how did we come about getting this? It's primarily a case of just observing what is the exact computation that's being done. In other words, writing down the equations and finding that by grouping terms together, you can simplify the equations to a certain extent. Now, the most important question, why was this useful? If you count the total number of hardware resources, what you find is we have 1, 2, 3, 4, 5, and 6 multipliers here in total, and the number of adders that we have is 1, 2, 3, 4, 5, 6, and 7. In other words, I'm assuming that the complexity of an adder and a multiplier, or rather an adder and a subtractor at least, are the same. So I have 6 multipliers and 7 adders. What did I have to start with? Over here I had 8 multipliers and 6 adders. In the new architecture I have 6 multipliers and 7 adders. So as long as the cost or area or whatever is the primary metric that you are concerned with of a multiplier is less or is greater than that of an adder, you will find that the resulting hardware that you have got by using this new structure occupies less area and most likely has a better critical path. Actually no, scratch that. The critical path will pretty much remain the same, but it will have a lesser area simply because it has fewer multipliers than the original design, which required 8 multipliers and 6 adders. So this is one example where we can make use of the parallelism, but combine that with something else which was done in order to optimize the equations that have been written down for the FIR filter and thereby get a better implementation of the final result. This is not always possible for all kinds of parallel architectures. The general kind of structure where we have x of n going through a serial to parallel compute and then parallel to serial to get back y of n, it may not always be possible to reduce the complexity of the compute in the middle. That requires additional insight into what kind of operations are being performed, in this case the FIR filter, and that is what we have made use of over here.